Hello my dear student friends, welcome back to my next lecture, that is on mass transfer coefficients in turbulent flow. By this time you understood the importance of the mass transfer coefficients or the need of estimation of mass transfer coefficient, particularly when you talk about the flow in turbulence or the turbulent flow. One cannot use the diffusion coefficient for the estimation of mass flux. We need to have some sort of a coefficient for the estimation of flux, and that coefficient what we call as a mass transfer coefficient. And as we understand, as we know, it is not easy to understand the behavior of a fluid flow in a turbulent flow. As we know, the turbulent flow is characterized by the fluid particles which are irregular in shape and irregular in direction as well as the time. And so what one can imagine, the turbulent flow is imagined to have a larger, consists of a lumps or a chunks or a disc of a different sizes. And as we discussed earlier, it is not easy to predict the behavior of these eddy movements. And when it is not easy to predict the behavior of the eddies, so it is not easy to estimate the mass transfer coefficients in the turbulent flow. So what we need to have, we have to have a mass transfer coefficients, or we have to estimate the mass transfer coefficient experimentally. For all situations and all geometries, it is not possible for the estimation of mass transfer coefficient, because we are coming across several flow conditions. Maybe we have a Reynolds number of 2, maybe we have a Reynolds number of 3, maybe we have a Reynolds number of 1000, maybe we have a Reynolds number of 10,000. So there are several Reynolds number, and when it is when you have several of the Reynolds number, and when you have several of the Reynolds number, it is not possible for the estimation of mass transfer coefficient at all Reynolds number. And at the same time, we are going to come across different flow geometries. Flow geometries in the sense, maybe we have a square, maybe we have a rectangular, maybe we have a sphere, maybe we have a cylinder, maybe we have some sort of irregular shapes. So when you have so many shapes and so many flow conditions, one cannot estimate the mass transfer coefficients in a turbulent flow experimentally. So what we have to do, we have to develop a theory. Based on that, one can estimate the mass transfer coefficients in the turbulent flow. Or sometimes what we are going to do, we are going to take the knowledge of the other transfer process for the estimations of mass transfer coefficients in the turbulent flow. And there are several theories are proposed to predict the behavior of the flow in a turbulent flow and estimation of mass transfer coefficient. Like we have a film theory, we have a penetration theory, we have a surface renewal theory, we have a combination of film and surface renewal theory, but all these theories are highly speculated, are continually being revised. So what one has to do now, whenever you are interested to estimate the mass transfer coefficients, not only solving of equation of continuity, or not only understanding about the continuity equation, one has to understand about the fluid flow. And if somebody wants to understand about the fluid flow, there is need to solve the equation of motion. So we have to solve the equation of motion, then you have to solve the equation of continuity, and this is what we have seen in the last class when we have discussed about mass transfer from a gas phase into the falling liquid. There we have taken the help of equation of motion, we have taken the help of equation of continuity, and this equation of continuity and equation of motion are solved simultaneously to get an equation for the concentration profile. From this concentration profile, what we did is we tried to estimate the flux, then we have estimated the mass transfer coefficient. Similarly, when you talk about the turbulent flow, also we have to solve the we have to understand about the fluid flow, and when you want to understand about the fluid flow, then we have to solve the equation of motion. So it is necessary always to solve the equation of motion, and this has to be clubbed with the equation of continuity, and these two equations can be solved simultaneously to get a mass transfer coefficients in the turbulent flow. And as we discussed, in the case of turbulent flow, we have eddies, and this eddies of size varying from a very small size to a very, very big size. And the largest eddy, which may be almost size of your pipe radius, maybe a smaller eddy consists of 1,000 or more molecules. And this larger eddies contains only 20% of your turbulent kinetic energy, and the medium so-called energy molecules, medium so-called energy containing eddies, make the largest contribution to the turbulent kinetic energy. So we have a larger eddies, we have a medium size eddies, we have a small size eddies, and the larger eddies, maybe the size is more or less equal to your pipe radius, maybe medium size eddies, maybe a smaller eddies which may contain more than 1,000 molecules. And now what is happening? The smaller eddies will break down, forms the molecules, and dissipates and because of the viscosity. And at the same time, the smaller eddies re-energized from the larger eddies, or maybe get some molecules from the larger eddies. So there will be some sort of equilibrium is existing between the smaller eddies, medium sized eddies, and the larger eddies. And this turbulent flow, which may be right or wrong, can be represented similar to the Indian political parties. When you look at the Indian political party, the political party may be bigger, and during its path, or during its during the time, the bigger party, maybe people are coming out from the bigger party, making a small parties, and these small parties again join in the bigger party, maybe a bigger party again broken down into a smaller parties. So this process is going to continue. So similarly, when in the case of turbulent flow, we have eddies, the bigger eddies will be breaking down into a medium sized eddies, maybe medium sized eddies into a smaller sized eddies. Again, these smaller sized eddies are re-energized to form a bigger eddy. So this is going to continue. And when you look at the time average velocity, there will be, as we discussed, there will be 3 directions: x direction and y direction and z direction. So when you talk about the x direction, there will be time average velocity, and this time average velocity we called as a ux. But when you look at the turbulent flow, this is not a average velocity. Maybe we can have this sort of a velocity profile we are going to see. Maybe at a particular location, if you are going to look at this horizontal line is the average velocity, but at any instant of time, the velocity may be higher than the average velocity or may be lower than the average velocity. So we call it as a velocity, that velocity we call it as an instant velocity, and this instant velocity is given by ux plus uix bar, where uix bar is called as the deviating velocity or the fluctuating velocity. Deviating velocity or fluctuating velocity. So, and there will be a positive deviating velocities, or maybe there may be a negative deviating velocity. And some of these positive and a negative deviating velocity, because there are some positives and some negatives, so some of this deviating velocity or the fluctuating velocity is going to become 0. However, the square root of the deviating velocity or the fluctuating velocity will not be 0. The square root of deviating time average of uix bar will not be 0. And we say the flow is isotropic flow if ux bar is equal to uy bar uz bar, and this flow is said to be isotropic flow, and what we said is this is ux bar, that square of your deviating or fluctuating velocities, and if these 3 velocities are same, then one can call it as a isotropic flow. Now we have a person called as a Kolmogorov, what he did, he has given some equations for the estimations of your velocity ud and length, a characteristics length, we call it as a LD, as a function of power unit per unit mass. As we know, fluid is flowing when you supply power, and power given per unit mass of the fluid, that is nothing but P by M, and when you give that power per unit mass of the fluid, then one can assume that there is the formation of the eddies, and one can estimate the velocity ud bar and length, characteristic length LD, and what he has given ud bar is equal to nu P Gc divided by M to the power of 1 by 4, and the characteristic length LD is equal to nu cube M divided by P Gc to the power of 1 by 4. As you know, each one is having its usual meaning, where nu is kinematic viscosity and P is the power that is given, and Gc is the universal constant, and M is the mass of the fluid. And if one can eliminate the nu between these two equations, one can write P into Gc by M is equal to ud cube by, so that means if one can know the power and mass, power that is given to the fluid and mass of the fluid, if you know, then we can find out the ud, where ud is the velocity and LD is the characteristic length. This is applicable for the smaller size eddies. So, and when you talk about a system where the system equilibrium is existing, equilibrium means we have a larger eddies, as we said, we have smaller eddies and we have a medium size eddies. So this medium size eddies lose its energy and the smaller eddies are going to grow, and at the same time the smaller eddies are going to break down or broke down into a smaller particles. So what is happening, there will be equilibrium existing between the medium size eddies and a smaller eddies, and whatever the energy lost from the medium size eddies, which is gained by the smaller eddies. So if that is the case, one can write this sort of equation even for the medium sized eddies, and for the medium sized eddies, P into Gc divided by M is equal to A U cube by L D, where A is the constant. This is applicable for the medium sized eddies. What I said, so whatever the energy that is lost by the medium sized eddies, it is gained by the smaller eddies. So we are applying this sort of a relationship for the smaller eddies. So we can have the relationship, similar sort of a relationship for the medium sized eddies, and the same relation we have written, only the difference is we have written some constant, and that constant one has to estimate the experimentally. So this is the little story about the turbulent flow, and why we are discussing about this fluid mechanics here. As we said, when you want to solve the equation of continuity, we need to understand about the equation of motion, and one has to understand about the fluid flow, and that is what we are discussing about little. This is already you learned in your moment and transfer course or a fluid mechanics course, and just I have repeated the same thing here, nothing else I have done it. And now if you look at the situation, a pipe consists of a dish, maybe this is the pipe, this is the center of the pipe, and maybe we have this is the one eddy, maybe this is another eddy. Why I am writing the zigzag shape? As I said, the eddy may be whatever the shape it may be. So we have a x direction and we have a z direction. We have a z direction, we have a x direction. Maybe we can say this is the location 2, maybe this is the location 1. And when you see the location 2 and the location 1, the distance, maybe you can call it as some distance, we can call it as a delta z. So what is happening, and here we can have some sort of instantaneous velocity, or the fluctuating velocity, or the instantaneous velocity uz bar, and maybe this is the uz bar. And now during this contact, this smaller eddy, maybe there may be a transfer of this eddy, or there may be a transfer of molecules from this eddy to this eddy, and at the same time there is a transfer of molecules from this eddy to this eddy. So what is happening? The eddy is moving, this eddy is also going to move, and this velocity ux, delta ux, and maybe if any concentration difference is also there, we can write it as a delta C, and any temperature difference is there, that can be written as a delta T plus delta T. So similarly you can write it as ux, and here you can write it as a, and this is, we can write it as a CA, and this is you can write it as a TA, maybe T or TA. So what we can say, I have a two location, I have a fluid which is flowing through the pipe, and maybe we have the flow is taking place in the x direction, and the other direction we have a z direction, and the third direction which is a perpendicular to your blackboard, and what we have a two eddies, let's say location 2 and location 1, and maybe the velocity in the z direction at location 2, maybe you can call it as some sort of uz prime, and the location 2 maybe uz prime. This is the there will be a difference in the some fluctuating velocity or maybe a deviating velocity, and these eddies, what is happening, this eddy will be moving here, this eddy will be moving here. So there is an interchange of the molecules are going to be occurs. So when there is an interchange of the molecules are going to be occurs, so the velocity at this location may be different from the velocity at this location. At the velocity at location 1 may be different from the velocity at location 2. So, and what we can say, when a equal volume of the fluid is moving from the location to the location 1, and at the same time there will be equal volume of the fluid is locating from transferring from the location 1 to the location 2, and the velocity at location 1 little higher than the velocity at location 2, and what we are going to define, a difference in this velocity, you call it as a delta ux, and this delta ux is equal to L into dux by dz, and where this L is defined as Prandtl mixing length, this L is defined as Prandtl mixing length, and this Prandtl mixing length is defined in such a way that ux bar is equal to delta ux, that is equal to minus L into dux by dz, and what this Prandtl has assumed that the eddies retain their identity during the transfer. Like for example, you have eddy here, we have another eddy here. So during the transfer, the eddies retain their identity, but they will be blending at a new location, and that is what this what do you call it, is the Prandtl theory is going to say. So the Prandtl theory is going to say the eddies retain their identity during the transfer, but it will be blending at a new location at maybe, and that is what is happening. This is the thing, and this is similar to what things are happening when somebody is moving from one party to the other party. During its movement, he is going to retain his identity, but when it reaches to the, when he joins in the new party, where he blends with the, he mixes or he blends, whatever you call it, so he loses its identity, but during the transfer still he maintains its identity, which is similar to the Indian political party, what I said, the fluid flow in the turbulent flow, which is just similar to the Indian political parties. So what we can say, we have a difference in the velocities, we have a different velocities. And now when you talk about mass velocity of interchange is equal to rho u z I bar, and whenever this mass velocity of the interchange is there, that means this is the thing that is happening, and obviously there will be a momentum flux. Our momentum flux, we call it as a shear stress. This momentum flux is equal to rho into uiz bar and multiplied by uix bar. This is the mass velocity, and because of there is a mass velocity of the interchange, and there will be associated to this mass velocity, there will be a momentum flux. So this momentum flux that is happening in the x direction, so rho uiz bar uix bar, and average shear stress due to the turbulent flow can be written as tau turbulent Gc that is equal to rho uiz bar uix bar mod, and this can be written as rho uz bar average of instantaneous velocities, average of deviating velocity and average of deviating velocity in the x direction, and this will becomes rho ux bar square if one can assume that uz bar, that is the fluctuating velocity in the x direction, is same as the fluctuating velocity in the x direction. So one can write rho into ux bar, and this can be written as definition of your Prandtl mixing length and your ux bar rho L square d u x by dz whole square. And do you understand on it? So there is a mass velocity of the interchange. That mass velocity of the interchange is given a rho into uiz bar, and whenever there is a mass velocity associated to this, there will be a momentum flux, and that momentum flux is nothing but this, and average shear stress due to the turbulent flow is, so that is nothing but tau turbulent gc rho into mod of uiz bar uax bar, that is also equal to rho into average of square root average of your fluctuating velocity in the z direction, fluctuating velocity in the x direction, that can be written as rho into ux bar whole square, and according to your Prandtl mixing length, ux bar can be replaced with minus L into dux by dz, and once if you substitute this, this is going to become like this. So but when you talk about a system where there will be a molecular movement, there will be turbulent motion, or maybe there is a eddy moment. So the total shear stress in a system where we have both laminar flow as well as the turbulent flow, and that can be written as mu dv x by dux by dz plus rho into L square dux by dx dz whole square. This is the flux shear stress due to the laminar flow. This is the shear stress due to the turbulent flow. And this is applicable whenever the fluid is the Newtonian fluid. So when the fluid is the Newtonian fluid, and when it is flowing through maybe any geometry, and we are going to come across laminar flow, we are also going to come across a turbulent flow, and the total shear stress is some of the shear stresses, that is a shear stress due to the laminar flow and shear stress due to the turbulent flow. So this also can be written as what one can write minus mu rho L square dux by dx by into dux by dx. And now we came to an important point or important conclusion, and this important conclusion is nothing but this is the term, and this term we call it as a eddy momentum diffusivity. And this eddy momentum diffusivity, what we can write, minus mu by rho plus L square d rho ux dx plus d rho x by dz. This is the term we have. As we said, we have a mass velocity due to the interchange, and associated to this there will be momentum flux, and the average shear stress due to the turbulent flow can be written like this. So in a given situation, both laminar flow as well as the turbulent flow are existing, so this can be written like this, and little reorganizing it, we are going to come to this equation. Further, what we are going to do, we are going to define, we are going to divide with rho, and rho can be taken out, and this is going to become tau gc. And as we know, this is nothing but kinematic viscosity, and this whole term is called as EV, d rho ux by dz. And kinematic viscosity, we can also call it as a momentum diffusivity, and this uv is called as the eddy moment and diffusivity. Already if you know about this, it is well and good. Otherwise, we call this as a moment and diffusivity, and this we call it as a eddy moment and diffusivity. And this moment and diffusivity is the property of the material, property of the fluid. But whereas EV, that is eddy moment and diffusivity, it is not the property of the material, it is the property of the flow. That means if you are going to change the flow conditions, or if the flow velocity, flow field is going to changes, your dux by dx is going to changes, your EV is going to changes. It is easy to tabulate the values of nu for all fluids, but it's not easy to tabulate the values of UV, because there are several of flow conditions we are going to come across. As I said earlier, we may have a Reynolds number of 1, we may have a Reynolds number of thousands and thousands. So, and that is where you cannot have any tabulated values, literature values for the UV, but whereas we have the literature values for the nu. That means if I say my fluid is the water and my temperature is this, maybe you can go to the any maybe a Perry's handbook and we can find out what is the kinematic viscosity or moment and diffusivity. But if you say my fluid is the water and my temperature is this, my Reynolds number is this, then we have to say this is the UV value, and at the time you have to also specify what is your geometry of the system. So what we can say, my fluid is water, my temperature is this, my Reynolds number is this, and my geometry is this. So if you specify all these 4 conditions, then I can specify what is the value of UV, and it is you can understand so very easily. We have infinite number of such type of points, and it is not possible to tabulate the values of UV. So that is the reason. So this moment and diffusivity is the property of the fluid, whereas this UV, eddy moment and diffusivity, is the property of the flow. And that is where what one has to do, we have to do something for the estimations of EV, and there are several of the theories and several of the equations which are available for the estimations of UV. Right? Any doubt we have, we can discuss. And this is where we are discussing about, and this is the important thing. That is where if this is not there, then we need not to study about this much of transport phenomena. Just one can estimate the shear stress, that is nothing but kinematic viscosity or the moment and diffusivity multiplied by the velocity gradient or the momentum gradient. So, but the thing is, we are going to come across a turbulent flow, and this UV is the eddy moment and diffusivity, which is a function of flow condition, flow geometry. So it is not easy to tabulate the values for all the conditions. That is the reason. So it is not so simple to evaluate the values of EV. So similar to that, when you talk about the mass transfer, when you talk about the NA, that is the mass flux, and this mass flux are the maybe NA, or we can say JA is equal to minus DAB, where that is the mass diffusivity, and that is multiplied plus EM, that is what we call it as the eddy mass diffusivity, multiplied by dCA by dZ. We have a shear stress equation which is similar to that. We have a mass flux equation or the molar flux equation, where the molar flux equation we have a DAB plus EM into dCA by dZ. So DAB, as you know, diffusivity, that is the property of the fluid, whereas EM, it is not the property of the fluid, it is the property of the flow. And so as whatever the explanation that we have given for the EV, similar explanations one can give for the EM. It is not easy to tabulate the values of EM. So estimation of flux in the case of turbulent flow, it is not that easy. That is where this DAB plus EM clubbed together, we call it as a special coefficient. That is what we said is a mass transfer coefficient. Then when you talk about the heat flux Q, that is similar to that, K plus rho Cp maybe EH plus dt by dz, that is also can be written as minus K by rho Cp plus EH plus d into rho Cp into T divided by dz. So here K by rho Cp, we call it as a thermal diffusivity alpha. Again, it is a property of the fluid, whereas this is nothing but eddy thermal diffusivity, which is a property of the flow. So at this stage we can appreciate the importance of this EM, EV and EH, and appreciate the importance of these three, and without these values one cannot estimate the shear stress or the mass flux or the heat flux in the turbulent flow. We should know the values of EV, EM and EH. So what we have to do, we have to estimate, we have to understand how to estimate these values. So there are several theories are proposed to estimate these values. Before discussing about these theories, maybe one can look at how to estimate these values when the fluid is flowing in a pipe in a turbulent fashion, right? And I don't want to discuss much about all these things, but what I want to tell you, this is what you have studied already in the fluid mechanics of course. We have EV by nu, where EV is nothing but eddy momentum diffusivity divided by momentum diffusivity, that is equal to Z plus divided by K to the power of 3, where Z plus is the dimensionless distance. Z plus is dimensionless distance from the wall. As we said, just repeating again, if one wants to estimate the heat flux, momentum flux or the mass flux in the turbulent flow, we have to know EV, EM, EH values. And we are discussing about a simple situation where fluid is flowing in a pipe in a turbulent fashion. And if that is the case, maybe we have a universal range equation, so what you have studied in your momentum balance momentum transfer course, and just I am trying to reproduce the same thing here. EV by nu, just to recapitulate what we have studied earlier, EV by nu is equal to Z plus by K whole cube, and where EV is nothing but eddy momentum diffusivity, nu is a momentum diffusivity, Z plus is the dimensionless distance from the wall, and this Z plus can be estimated from d by 2 minus Z u bar by nu f by 2 to the power of 0.5, where D is the diameter of the tube, where Z is the distance from the center of the pipe, Z is the distance from the center of the pipe, u is the velocity, nu is the kinematic viscosity, f is the what you call it as the friction factor to the power of 0.5, and this K is in the range of 8.9 to 14.5. So what we can do, just when you talk about the fluid flow in a turbulent flow, just if you know the Z plus value, where Z plus is the dimensionless distance from the wall, that means if location is changing, your Z plus is going to change. If Z plus is going to change, your UV is going to change. If UV is going to change, your momentum flux is going to change. So what one can say, this EV is a function of flow conditions, and it is a function of the, obviously when you talk about the function of flow condition, and it is a function of the location. So once if you know the Z plus value, one can estimate from this equation by knowing about the value of Z, and if you know the value of KV, and if you know the value of nu, that is the kinematic viscosity, one can estimate the EV value. And similarly one can write ED by nu, that is equal to EH by nu, that is equal to 0.00090 Z plus whole cube divided by 1 plus 0067 Z plus whole square to the power of 0.5. So this is the equation one can estimate the kind eddy momentum diffusivity. These are the equations one can estimate the mass eddy diffusivity and thermal eddy diffusivity. So once if you know the E plus value from this equation, one can estimate the what do you call it, ED and EH. Suppose if you when Schmidt number and a Prandtl number equal to 1, your EU is equal to EM, that is equal to ED. And if SE and the Prandtl number are greater than 1, ED by EV and EH by EV will vary as a function of the location, and these values are given by 1.2 to 1.5, right? And suppose what do you want to say? Your Schmidt number, this is what already we have defined. Prandtl number, this is what we have defined, know already. So if Schmidt number is equal to Prandtl number, that is equal to 1, your eddy moment and diffusivity is equal to eddy mass diffusivity, and that is equal to eddy thermal diffusivity. Eddy thermal diffusivity. So if one can know the value of either EV or EM or EH, other two values can be estimated. Similarly, when you talk about the Schmidt number and the Prandtl number, which are values are greater than 1, and ED and EV and EH by EV are a function of relocation related to the wall, and the values are in the range of 1.2 to 1.5. That is, if you know the EV value, maybe one can assume either 1.2 or 1.3 or 1.4, and one can estimate the ED value. So similarly, EH value can be estimated. And now you have reached to a very important conclusion or a very important point. Suppose if you know the behavior of, if I understand one transfer process, that transfer process can be aired, or that transfer process can be taken help for the predicting the behavior of the other two transfer processes, either maybe heat transfer process or the mass transfer process. So this is the very, very important thing. And if a Schmidt number is equal to Prandtl number 1, then these three are equal. If a Schmidt number or the Prandtl number are greater than 1, these two are not equal. These three are not equal. However, the ED by UV and EH by EV is 1.2 to 1.5, or what one can say, your ED is equal to EH. This is the one more important conclusion we can write, or one more important thing that can be bring into the thing. That is, if you know the eddy thermal diffusivity, so from that eddy thermal diffusivity, one can estimate the eddy mass diffusivity. Once if you know the eddy mass diffusivity, it is easy to estimate the mass flux. And that is where what we can say, we are taking the help of the heat transfer process, and we are going to estimate the mass fluxes. Or what we can say, there is an analogy which is existing between the heat transfer, mass transfer, and the momentum transfer. And these analogies can be used whenever we don't understand the transfer process maybe in the mass transfer. When you don't understand the mass transfer process, maybe one can take about the heat transfer process. It is easy to understand the heat transfer process, so we can take the help of the heat transfer process for understanding about the mass transfer process. And this is the beauty of the analogies. And what we have studied in the momentum transfer course, everywhere you understand about the universal equations and other things, where we are interested to find out the EV values for different situations. And once if you know the EV values, you can estimate the ED values as well as the EH values. So one can estimate the mass flux as well as the heat flux. And except liquid metals, in most of the cases, the values of ED and EH are equal. And we are going to come across another important definition, that is what we call it as the diffusional sublayer. And the diffusion sublayer is defined as, we have a molecular diffusivity and we have a eddy diffusivity. So the diffusion sublayer is defined as place where molecular diffusivities are more than the eddy diffusivities. So that means your nu is greater than EV, or your DAB is greater than ED, or your alpha is greater than EH. So if that is the case, that layer we can call it as a diffusion sublayer. And it is so easy to understand, like when the fluid is flowing over the pipe, as we know, near the wall, the flow may be in the laminar zone, and when the flow is in the laminar zone, that means your momentum diffusivity or molecular diffusivity is more important or more dominant than the eddy diffusivity. And places where, that means near to the wall, the molecular diffusivities are greater than the eddy diffusivities, and those places we call it as the diffusion sublayer. And now, I think if you can understand what I'm stressing or what I'm telling you, very important concept. So if you know this eddy diffusivities for a one transfer process, we can estimate the eddy diffusivities for other transfer processes. And this sort of a relationship, if we can establish, then we call it as a analysis. And these analysis we can discuss more in the module number 13, where we have a different types of analysis. We have a Reynolds analogy, we have a Prandtl analogy, we have a Van Karman analogy, or maybe we have a Chilton-Colbert analysis. So we have different analogies we have, and those analyses we are going to discuss in the module number 13. And now the next thing is a theories of mass transfer. And now, as we discussed already, there are some theories which are available for the understanding about the flow behavior, or the for the estimation of mass transfer coefficients in the turbulent flow. Those are called as the film theory, penetration theory, surface renewal theory, film and combination of film and surface renewal theory. Maybe we have surface structure theories. Various theories are available. As we discussed already, these theories are highly speculated, and these theories are continuously changing. And one of the theories, that theory, most important theory is the film theory. And this film theory, what it says, so when a fluid flows turbulently past a solid surface, a fluid flows turbulently past a solid surface, and with mass transfer is occurring either from the solid to the fluid, or fluid to the solid, or maybe we can assume that the mass transfer is occurring from the solid to the fluid. Then if you look at the concentration distance relation, the concentration of solute is a very high near the wall, and this concentration is going to be changing. And now if you can plot a graph between Z, distance from the wall, versus a concentration, right, and we are going to have this sort of a profile. And this profile already we have discussed when we began our chapter on mass transfer coefficient. That is what like now, as another case, what we have said, suppose if I have a liquid pool of liquid, maybe a pool of water is there, and the air is flowing over that fluid of flow of over the water. Now what is happening? Water is evaporating, and there is the interface between the air and the water. The concentration of the water vapor at the interface is equivalent to your partial vapor pressure at the existing temperature. Then if you look at if you take the samples away from the surface, the concentration is going to decreasing and decreasing, and when you plot a graph between concentration versus distance, the concentration versus distance curve is going to be like this. So what this film theory is now is assuming that a fictitious film is existing, right? This is the data. So what this film theory is going to say is a fictitious film is existing, and this fictitious film thickness is ZF, and the concentration variations are only there in this film, which is adjacent to the wall, and away from the wall there is no variations in the concentration. Or what we can say, so what the film theory is going to say is, this is actual experimental values, and this is the given by the film theory. What this film theory is going to say is, the concentration variations are going to be there only in the small film, which is adjacent to the surface, and that variations of the concentrations are going to be there in only that small film. And if you away from if you just cross that film, there will not be any variations in the concentration. This is what we have discussed earlier. The concentration, large concentration gradients are going to exist in the laminar flow, and the small concentration gradients are going to be existing in the turbulent flow. But what this film theory is assuming, that there is no concentration gradient at all in the turbulent flow, and whatever the concentration gradient that is existing only in the laminar flow. And this is the important theory, and this thickness we call it as a effective film thickness. This ZF we call it as a effective film thickness. And what it says, this theory is applicable, the film theory is applicable whenever the film is very thin. If the film is very thin, that means the amount of material that is retained in the film is a very small. The film thickness is very small. So that means the amount of material that retained in the film is a very small compared to the amount of material that is passing through the film. So if the film is very thin, one can apply the film theory. Just to tell you one example, as we discussed in the first module, there are several of the separation techniques, and one of the novel separation techniques are the membrane separation process. In the case of membrane separation process, I have a membrane here. I have two components, A and B. These two components has to be separated using this membrane. So both the components A as well as the B comes to the surface. But this membrane is will permeate only the component A of A, and the B is going to be rejected by the membrane. So the concentration of B at the membrane surface will be more compared to the concentration of B in the bulk. So what we can say, maybe if you can look at the profile, maybe this is the profile. The concentration will be very large in the it will be more in the, maybe I can put it in a different way, maybe you can understand this, right? So I have A and B, both A and B are coming to the membrane. A will pass through the membrane, the B will be rejected by the membrane, and now when B is rejected by the membrane, the concentration of B on the membrane surface will be more compared to the bulk surface. And if you are going to see the concentration profile, this will be the concentration profile. And if you can see this thing, and here the variations are very small, and only the variations are going to be there, large variations are going to be there at this place. So what the film theory is going to say is, what are the concentration gradients are existing, that concentration gradients are existing in a small film which is adjacent to the surface and above which there is no variations in the concentration. This is what the film theory is going to predict. And if you look at this actual experimental data and the data predicted by the film theory, there is so much of deviation is there, but still one can use the film theory, and this film theory is more applicable when the thickness of the film is very thin. And when the film thickness is very thin, amount of the B that is present in this film is a very small compared to the amount of B that is passing through the film. So that is the characteristics of a film theory. And the second thing is, film theory is assuming that the process is the steady state process, right? The process is the steady state process. The process is the steady state process means, right? And steady state conditions are going to be existing within the film, and even if the contact time is very less, the steady state conditions are going to be existing, and this is only happen when we have a higher DAB values. Steady state process. Then we have a bulk flow term. If you can look at your previous equations, Na is equal to Na plus Nb into Ca by C plus Ja, and this is what we call as the diffusion flux, and this is what we call as the bulk flow. And this bulk flow, right, in this case of film theory, the bulk flow is neglected. What we say, your Na is equal to just simply Ja. So this is the assumption number 1, this is the assumption number 2, and this is going to be applicable if film is very thin, right? And now this thickness of the film, whether it is the thin or thick, depends on the flow conditions, right? And now what we can do some steady state mass balance equation, and one can obtain a relationship for the DAB and the mass transfer coefficient, right? Like we have, this is the surface, this is the film, and the solute A is moving. This is the film of thickness ZF, and here maybe we can take a differential element whose thickness is delta Z. So some material is coming here, entering here, amount of material entering at location A, maybe we can say this is the distance Z from the wall. Some material is entering at a location Z, that is nothing but Na at Z, and some material is going to leave at Z plus delta Z, that is nothing but Na Z plus delta Z. and according to your mass balance equation, your input minus output is equal to accumulation. And we assumed that in the case of film theory, we assumed that the steady state conditions are going to be existing. So that means your accumulation term is going to become 0, and your input is equal to Na into Z multiplied by the area perpendicular to the flow. Area perpendicular to the flow. And output is nothing but ANA Z plus delta Z, and already just to inform again, this Z, the conditions are evaluated at Z. This means the conditions are evaluated at Z plus delta Z. So now we can divide with A delta Z, divide with A delta Z, and take delta Z tends to 0. And when you take delta Z tends to 0, this is going to become dNA by dZ, that is equal to 0. And when you neglect the bulk flow term, your Na is equal to Ja, that is equal to minus dAb into dCa by dZ. So this is going to become d square Ca by dZ square is equal to 0. And this equation can be solved using a boundary conditions. At Z is equal to 0, Ca is equal to Cai, and that is at the wall the concentration is Ca is equal to Cai, and Z is equal to Zf, Ca is equal to Cab, where Cab is nothing but a bulk concentration. Cai is the interfacial concentration, that is Z is equal to 0. At Z is equal to Zf, that is the film thickness, the concentration of a solute is similar to your bulk concentration, that is nothing but a Cab. So now we have a two boundary condition, we have a second order differential equation, and one can solve this second order differential equation using this boundary condition, and one can write concentration profile, and this concentration profile is equal to Cai minus Cab into Z by Zf. And if you look at this equation, the variation of Ca with respect to Z is a linear. That means this is the thing. As if that is nothing but your Z is equal to Zf. If you look at the Z is equal to Zf, this is going to become 1. Cai minus Cai is going to become 0, and we are going to be left over with the Cab. That is what the boundary condition 2. So if Zf is equal to 0, this is what we can write. And Ca is equal to Cai minus Cab. This is the linear equation, and one can predict the concentration profile. And once if you know this is the linear equation, once if you know the concentration profile, and we know that the flux Na is equal to minus dAb into dCa by dZ, where this derivative is evaluated at Z is equal to 0. This is going to become, if you can differentiate this with respect to Z and substitute Z is equal to 0, then we are going to get dAb by Zf Cai minus Cab, that is, as you know, the KL Cai minus Cab. Or comparing these two equations, the KL is equal to dAb by Zf. What the film theory is going to say is, for any solute, the KL is proportional to the dAb for a given flow condition, and it depends on the flow condition, the Zf value is going to change. But experimentally, it was observed that the KL is a function of dAb to the power of n, where n is ranging from 0.8 to 0.9. And what the film theory is going to say is, KL is proportional to dAb, but experimentally it was observed that KL is proportional to dAb to the power of n, where dAb n value is 0.8 to 0.9. That means the film theory is not properly predicting the mass transfer coefficient for the turbulent flow, But even then, nevertheless, even then, this is the one of the theory which is even today used for the estimations of the mass transfer coefficients in the turbulent flow. As I said, even today, even after existing of membrane separation process for a long time, what people use, people use the film theory. If you don't use the film theory, and if you are going to use any theory, the equations are going to become very complex, and solving of these equations are going to become very, very difficult. And just to tell you, sometimes this mass transfer coefficient or the heat transfer coefficients is called as the film coefficients. So this is about the film theory, and the next class what we are going to discuss, about the other theories which are reported in the literature. So thank you very much.